is Josh Durgin. I'm a developer of Ceph. I work for Inktank and Red Hat, although my opinions today are personal opinions, not expressing the company's opinions at all. So I'd like to talk today a little bit about storage protocols and how they work in OpenStack and where we can go in the future. So I want to talk first about iSCSI. What is iSCSI? Well, it's a protocol for block storage. It was created in the late 90s by IBM and Cisco, and it supports all kinds of different disk commands that you'd usually use for a local disk, but over Ethernet, and more recently, other kinds of fabrics. It supports the standard operations you'd expect, like read and write, and also some more fancy things like verifying reads and verifying the written data is actually there. And it's been standardized multiple times with many revisions over the years. So it's a very well understood interface. There's lots of things good about this. It has a very large set of commands. It supports things like persistent reservations, which enable high availability in a standardized way. And since it's a standardized interface, vendors and different products can interoperate without having to have any strange issues or make them specialized for each specific product. Things like data integrity, or diff, is one of those more newer features in the command set, which is continuing to evolve. But the command set is still based on the basic idea of sending commands to a SCSI disk. So because the command set is standardized, it's very easy to implement and work with other platforms. However, this also means that it's very hard to evolve. And after 20 years of evolution, there's lots of new commands supported, but at some point you hit limitations for what you can do. So for iSCSI, the general model is that there's a target, or the server, and an initiator, or a client. And the initiator just sends these SCSI disk commands over to the target. And so the client is kind of limited in what it can do based on the SCSI standard. So that kind of limits where innovation can happen at the storage level. The other thing that's not standardized by SCSI is the management layer aspect of it. So SCSI defines basically the data path, but not things like creating or deleting entire volumes or snapshotting and cloning them. So let's talk a little bit about how high availability works in SCSI and where that came from. So when iSCSI was created, the kind of state-of-the-art of high availability at the time was using large, expensive SAN arrays, or maybe some commodity hardware, but using RAID and many redundant NICs or many redundant other pieces of hardware for reliability. Instead of trying to build reliable software, a lot of the burden was pushed onto hardware and RAID controllers. So with iSCSI, high availability basically is the old school style of HA, where you have maybe two paths to two different servers, and you have some kind of service monitoring those paths, and if one goes down, failover happens, and an external agent switches the iSCSI initiator from accessing one server to accessing a different one. Now, one of the things this means is that you can't have a cache on the SCSI target if you want high availability, because when you switch from one server to another one, that cache isn't there on the second server. So that makes high availability for SCSI targets a lot more complex as well, unless you can sacrifice that performance with extra cache there. So let's compare that where we came from with at the time of iSCSI to where storage is today. Today we have petabytes and petabytes of data, and scale-out storage is very, very common. We have lots and lots of commodity hardware, many hosts, and lots of software is written around trying to hide those failures from the user of the software, rather than making the storage protocol and external agents handle high availability. They're more complex but more easy to use ways of handling things. So in modern distributed systems, high availability and consistency are sort of native features. Rather than waiting for an external service to go and check is this server alive or is this server alive, and switch from one to a different server. Distributed systems tend to actually implement this themselves and handle these failures internally without any client interaction or any client external agents needing to handle client changes of IP addresses or anything like that. Another big factor in this is the general use of commodity hardware more recently. And in the last 10 years, lots and lots of folks have seen the vast benefits of cheap commodity hardware to avoid vendor lock-in, to get the best kinds of hardware and scale different kinds of resources independently from what they could with large, expensive SANs. So clients in distributed systems are often actually more complex and much more intelligent than an iSCSI client would be. Because distributed systems tend to actually handle high availability themselves and detect talk to many different servers at once rather than just a single target, the clients have to be a little bit more intelligent and know internally when things fail and when to talk to different servers. So not just talking, it's not like iSCSI multipathing, which is talking to maybe one or two different servers at once. With distributed systems, you're actually talking to maybe hundreds or thousands of servers at once. And because we have these intelligent clients, this also enables many more optimizations. You can have caching on the client. You can have all kinds of things like management features like snapshots that occur instantly and while a guest is still running or while something is using that storage. Because the client is aware of that snapshot happening, that can happen while everything is online, even when there are caches in the way. So with all these extra features that advanced and intelligent clients can bring, this gives a tremendous advantage to open source projects. Since proprietary vendors tend to be stuck with a standardized interface like iSCSI, they can't take advantage of more advanced distributed systems features in their clients. So they have to go through an extra hop of going through an iSCSI target, which can't do any caching itself, and then to whatever the backend they have. But they still have to manage all this complex, old-school high availability of the iSCSI target and the initiator failing over, which you don't get with modern open-source distributed storage systems. So things like Ceph and ClusterFS, when you're accessing a block device through QEMU with those pieces of software, QEMU is actually talking directly to all the storage servers through their libraries. So it's not going through the host at all, and it's not using any kind of iSCSI. So this is how things work today with OpenStack. Cinder, when you attach a volume, is just going to tell Nova if it's a Ceph volume, here's the pool and image name for that Ceph volume. And QEMU will go and actually access the volume directly without actually having to go through the host at all. Whereas if you're using something like LVM or a SAN, Cinder has to coordinate with Nova, set up an iSCSI initiator on the Nova side, and the high availability setup there just isn't automated yet at all with OpenStack. So that's the general overview of iSCSI and Ceph and how it works. If there are any questions, I'd love to hear them. On IRC, you can find me as Durgin on Freenode, and there's my email address. Thank you.